Imagine our Earth, not as we know it, but gripped by an icy rain. Vast ice sheets, kilometers thick, sprawled across continents, reaching far beyond the polar regions. This wasn't a scene from a fantasy novel, it was our planet's reality during the ice ages. These periods of intense cold spanning millions of years have left an indelible mark on our world. These cycles, driven by subtle variations in Earth's orbit and tilt, dramatically impacted the planet's landscapes and its life. Entire mountain ranges were carved, valleys gouged out, and vast lakes formed. These changes reshaped the very face of our planet, influencing the course of rivers and the distribution of land and sea. Understanding these past periods of extreme cold offers us a unique perspective on the power of our climate system. By studying these icy chapters in Earth's story, we can glean vital insights into our planet's past, present, and future. Ice, in its immense power, has been a master sculptor of our planet's surface. As ice sheets advanced during glacial periods, they acted like giant bulldozers, scraping and carving the land beneath. The weight of the ice, often miles thick, depressed the Earth's crust, creating vast depressions that, after the ice melted, filled with water, forming some of the world's largest lakes. The Great Lakes of North America, for instance, owe their existence to this glacial legacy. As glaciers retreated, they deposited vast amounts of rock debris known as glacial till across the landscape. These deposits created rolling hills, fertile plains, and even islands, fundamentally altering the topography of entire regions. From the rugged peaks of the Alps to the sweeping plains of North America, the fingerprints of ice are everywhere, a testament to the transformative power of these frigid epochs. Earth's climate is a dynamic system in constant flux. Over millions of years, our planet has swung between periods of intense cold, the ice ages, and warmer interglacial periods. These cycles are driven by a complex interplay of factors including variations in Earth's orbit, solar radiation, and atmospheric composition. One key driver is Earth's orbital eccentricity, shifting from nearly circular to slightly elliptical over about 100,000 years. This change affects the amount of solar radiation Earth receives, influencing global temperatures. Another factor is Earth's axial tilt, which varies over a cycle of approximately 41,000 years, determining the intensity of seasons. Understanding these cycles is crucial for comprehending the rhythm of ice ages and the transitions between glacial and interglacial periods. The onset of ice ages presented a formidable challenge to life on Earth. As temperatures plummeted and ice sheets advanced, many species faced extinction. However, life, with its remarkable resilience, found ways to adapt and thrive in these challenging conditions. Some species migrated to warmer refuges, following the retreating warmth towards the equator. Others developed physiological adaptations to cope with the cold, like thicker fur, layers of blubber, or the ability to hibernate. The pressure cooker of natural selection during the ice ages also drove evolutionary innovation, with new species emerging better suited to the changing environment. The story of life during the ice ages is one of both challenge and opportunity, demonstrating the remarkable resilience of life on Earth. The impact of ice ages extended far beyond the regions directly covered by ice. During glacial periods, vast amounts of water became locked up in ice sheets, causing sea levels to drop dramatically, exposing large swaths of land. This created land bridges that allowed for the migration of animals and humans. The colder temperatures also impacted ocean currents, altering their flow and influencing global climate patterns. The thermohaline circulation, a global conveyor belt driven by differences in temperature and salinity, slowed down during glacial periods, impacting heat distribution around the planet. With less moisture available in the atmosphere, deserts expanded, while forests contracted, retreating to more hospitable regions. These changes in vegetation had cascading effects on ecosystems, impacting the distribution and abundance of plant and animal life. The last glacial maximum, around 20,000 years ago, serves as a stark example of the profound impact ice ages had on our planet. During this period, ice sheets reached their maximum extent, covering vast areas of North America, Europe, and Asia. In North America, the Laurentide ice sheet extended as far south as present-day New York City and Chicago, creating the Hudson Bay and the Great Lakes. In Europe, the Scandinavian ice sheet blanketed much of northern Europe, carving out the fjords of Norway and leaving behind a legacy of glacial lakes and deposits. The British Isles, once connected to mainland Europe, were separated by rising sea levels as the ice melted. The last glacial maximum serves as a compelling case study, illustrating the transformative power of ice ages. By studying this period, scientists can better understand the dynamics of ice sheets, the impact on global climate, and the response of ecosystems to such dramatic environmental change. Even though the last ice age ended thousands of years ago, its legacy is still visible today, etched into the landscape and woven into the fabric of life on Earth. From the shape of coastlines to the distribution of plants and animals, the echoes of these frigid epochs resonate in the modern world. Many of the landforms we see today, such as valleys, lakes, and fjords, were carved by glacial ice. The rolling hills and fertile plains of the American Midwest are the result of glacial deposits left behind by retreating ice sheets. The distribution of many plant and animal species also reflects the impact of past glaciations, leading to the diversity of life we see today. The study of ice ages offers valuable lessons for modern society, particularly in the context of current climate change discussions. By understanding how Earth's climate system has responded to past changes, we can gain insights into its potential future behavior. Ice ages demonstrate how changes in Earth's orbit, atmospheric composition, and ocean currents can have profound and far-reaching impacts on global climate, sea levels, and the distribution of life. Another important takeaway is the speed at which climate change can occur. This rapid change underscores the urgency of addressing human-induced climate change. As we grapple with the challenges of climate change today, understanding Earth's history of glaciation takes on a new urgency. It reminds us that our planet's climate is not static, but rather a dynamic system capable of dramatic transformations. The study of ancient ice provides us with valuable data on past atmospheric conditions, offering clues about the interplay of greenhouse gases, temperature, and the intricate workings of our climate system. The lessons from the frozen past are clear. Earth's climate is capable of dramatic shifts, and human activities are now a driving force behind these changes. By heeding the warnings from our planet's history and taking action to mitigate climate change, we can help ensure a more sustainable future for generations to come.